So, for quite a while, once the idea of chemical equilibrium was established, scientists wanted to figure out a way that they could sort of measure how a chemical equilibrium would work. They wanted to measure how many products there would be compared to how many reactants. And so, in an effort to do this, they came up with something called the concentration fraction. Now, the concentration fraction is also sometimes referred to as the reaction quotient. And up here we have a general chemical equation with coefficients A, B, C, and D, and reactants and products W, X, Y, and Z. And so the concentration fraction, or the reaction quotient for this general reaction, is equal to the concentration of both of the products raised to the power of their coefficient divided by the concentrations of the reactants, again to the power of their coefficients. So for example, if we had maybe the production of water, so if we had oxygen and hydrogen producing water, then our concentration fraction would be, or CF would be, so that should be a 2 there, would be concentration of water squared over the concentration of oxygen times the concentration of hydrogen squared. And those squarings are because we've got 2 hydrogens and 2 water molecules. We've got the coefficients of 2 in front of those substances. So that is what our concentration fraction is equal to. And so for this, it's obviously important to know that if we write y in square brackets like that, then that means that refers to the concentration of y in moles per liter. So yes, writing a chemical in square brackets refers to its concentration in mole per liter. So that is the concentration fraction. And so the concentration fraction can be calculated at any point in a reaction. So if we throw in a few moles of oxygen and a few moles of hydrogen and the reaction hasn't really started going properly yet, we can still calculate the concentration fraction at any time. However, it so happens that the reason that scientists came up with this specific concentration fraction expression is that when we reach equilibrium, once we put our oxygen and our hydrogen in together and the reaction reaches equilibrium, then our concentration fraction becomes a constant. So no matter how much oxygen and how much hydrogen we start with, once the reaction reaches equilibrium, our concentration fraction will always equal this constant number, K. So we might start with 5 moles of oxygen and 1 mole of hydrogen, let the reaction go to completion. And then once we're at equilibrium, let the reaction reach equilibrium. And once we're at equilibrium, our concentration fraction will equal some number K. Now, if we then repeat the reaction, but we use maybe 7 moles of oxygen and 12 moles of hydrogen, so completely different numbers, we'll end up with completely different amounts of our reactants and products, but this concentration fraction will still be the same once we reach equilibrium. So that means that K for this reaction is equal to H2O squared over oxygen times hydrogen squared at equilibrium. So it's equal to this expression when all of these concentrations are the concentrations at equilibrium. And so that there is our equilibrium law. So this thing here is our equilibrium law. And this is very important. So this number K is unique for every reaction. It's unique for every reaction. And it's equal to this expression here where we've got our products on the top and our reactants on the bottom. It's equal to this expression here when this expression is calculated at equilibrium. So for any no matter if we start with different amounts of reactants and products, then our actual amounts of oxygen, hydrogen, and water once we reach equilibrium will all be completely different. However, our concentration fraction, or our equilibrium constant, will still be the same once we reach equilibrium. And so K is what we refer to as the equilibrium constant. And so this number here allows us to find out lots of information about an equilibrium mixture, about a reaction mixture that has reached equilibrium. So when we're talking about our equilibrium constant, it's different for every reaction. It's different for different reactions. So we need to calculate it uniquely for every reaction. Also, it is constant for a reaction. That's why it's called the equilibrium constant at a given temperature. So at maybe 25 degrees Celsius, no matter what sort of mixture we have of oxygen, hydrogen, and water, K will be the same. However, if we change the temperature, K will be different. So those are the properties of this equilibrium constant, K. Now, let's do an example involving this idea of equilibrium constant. So we've got this regular general expression here for, we just have the products raised to the powers of their coefficients divided by the reactants raised to the powers of their coefficients, and that is our concentration fraction. And at equilibrium, when everything's at equilibrium and we then calculate our concentration fraction, then we get this concentration fraction equaling a constant number once we've reached equilibrium. So if we look at this example down here. So we've got this reaction here. We've got the production of ammonia from nitrogen and hydrogen. And we've got a bit of data about our reaction. We know the K value at a given temperature. We know the concentration of nitrogen in this given mixture that we're specifically dealing with here. We know the concentration of hydrogen in this given mixture, and we know the volume of this mixture. So here I've written units, and that is because units are very important when we're calculating K values, and we simply do that by looking at the number of the units. So if we have, for example, here in this equation, we've effectively got H2O times H2O like that over oxygen times hydrogen times hydrogen. And so we can see that our unit is we've got moles. We've got a molar solution times a molar solution over, we're going to have two values up here that have units of mole per liter. We're going to have 3 down here that have units of mole per liter. And so our final K value is going to have units of per mole. Similarly, down here, we're going to have 2 values of mole per liter on the top and 4 on the bottom. And for that reason, our unit for our constant is mole to the negative 2. And so it's very important if we're ever calculating a K value to include the units in that way. So now let's work out, what we want to do is we're going to work out the number of mole of ammonia that we have. So we want to work out the number of mole of ammonia, the N for ammonia. So first of all, we have to write an equation. So we know that K is equal to NH3 squared, ammonia squared, over nitrogen times hydrogen cubed. Now we sub in our values. So we're looking at how many mole in this mixture here, the mixture given by these parameters, at a temperature of 300 degrees Celsius. So if we sub in our values, then we know that 9.6 is equal to concentration of ammonia squared divided by 0.8 times 1.1 cubed. So what that gives us is that concentration of ammonia squared, if we manipulate this equation slightly, then we get the concentration of ammonia squared is equal to 10.2, and therefore our concentration of ammonia is equal to 3.2. So that is our concentration of ammonia, but we want to know the number of mole of ammonia. So we know that the concentration of ammonia, 3.2, is equal to the mole of ammonia over the volume of the mixture. And we know the volume of the mixture is 3.7. So that means the number of mole of ammonia is equal to 3.2 times 3.7, which is equal to 11.8 moles. So that's how equilibrium constant works. We basically draw up this equation at the start of any calculations involving equilibrium constant, and we can just substitute in the values that we know. However, we have to be aware that when we write this equation, these concentrations here refer only to the concentrations at equilibrium. If we're calculating a concentration fraction, it doesn't necessarily have to be at equilibrium, but if we're dealing with this K value, this expression here can only be calculated at equilibrium. So that's very, very important. And so any K value, any equilibrium constant or any K value has a unit based on the number of units of mole on the top and the number of units of mole on the bottom. So this K value this K value is unique to every reaction at a given temperature, and it allows us to really look, as we did here, at the amounts of our different substances that we have at equilibrium.